Good afternoon, everyone. It's my sincere pleasure to introduce Dr. Stephen Aumeier from Idaho National Laboratory. He serves as the Senior Advisor for Nuclear Energy Strategic Programs at INL. He's had over 3 decades of service in the National Laboratory system, which included a number of different positions. And he's a recognized expert and thought leader in technology, business, and clean energy strategies, which is very important to our talk today. He was also named in his current post in 2016 after serving for 6 years as Associate Lab Director, or ALD as they call it, for Energy and Environment, and Director for the Center for Advanced Energy Studies. He's also, before INL, just to summarize, he served for 10 years with Argonne National Laboratory, and we traded a few stories about Argonne West. So we were both there about the same time for a little bit. I was there for a little bit. But he also served for a time, as a lot of laboratory folks do, served in Washington, D.C. with the NNSA, National Nuclear Security Administration, which he helped establish national strategies to address radiological threats. So I can appreciate what you must have gone through with that service. He's an alumni of Merit by the University of Michigan, Department of Nuclear Engineering and Radiological Science. And he holds a PhD in nuclear engineering from the University of Michigan, as well as an MBA from the University of Chicago. So without further ado, please welcome Dr. Aumeier.
Well, thank you. I appreciate that. Am I speaking loudly enough? Good? Everyone fine? Okay. Sometimes I start rambling on and mumbling, so I'll trust you to give me a signal. So I want to start by thanking the University of Utah for the kind invitation, and the Utah Academy of Science and Engineering, SID in particular. It's been a great day. I've really enjoyed the discussion. Most importantly, I've learned. I've learned a bit. So so I was mentioning just when we got started, I really like the title, Frontier to Frontier, and I think that sort of sets a context for what I want to talk about today. And hopefully this will be a monologue followed by a lot of questions. So please think about the questions. Why frontiers to frontiers? 70 years ago, right around 70 years ago, is when the commercial nuclear energy industry really began. And it began with shipping port. It actually began before that with some really brilliant people wondering what this new technology, what this new science was going to bring the world. And that was really very much a new frontier. Nothing had been built, nothing had been engineered at commercial scale in the commercial nuclear energy field. There was still a lot to learn. There was a lot to learn about operations. There wasn't any regulatory framework put in place. That's a frontier, right? It is a brand new frontier. But I think what you'll see today is you're really at the forefront of a next frontier. And it's a frontier built on the shoulders of many mistakes, many learned processes, technologies that have been proven. But it's a new frontier, I think, in terms of nuclear energy's role in a world of 8 billion people. And I'd ask you to keep that in mind, 8 billion people. And that's why I think of this as a frontier to frontier. But you're certainly at the beginning of a new frontier, and we'll talk about why. So the objective, my objective, isn't to talk about details of technology or necessarily even the science behind it, but rather give one a framework and a context to ask questions, to think about the differences between what we had in the first frontier and what you might face in the next frontier, and understand some of the terminology that people throw around, even for engineers and scientists, that begins to, you know, I even step back, and I've been in this field for 30 years. I step back and think, what, you know, what are they talking about? Why does it matter? I'd like folks to walk away and be able to ask the question, why does it matter? What you're looking at. Why are we considering different types of technologies, if you can use that term, even types of technologies? Why do the technologies look different? And why do we care? So that's the objective. So who in the room is familiar with the National Lab System? Probably many of you. So I'm going to skip this. The Idaho National Lab, I have to tell you where I'm from. The Idaho National Lab is one of 17 multi-purpose labs. The important point is we are the nation's lead for nuclear energy within the National Lab System, not the only lab, but that also comes with a lot of other responsibilities and capabilities that the lab has, mostly in the national security area, in addition to nuclear energy. So we're just one of many. Lots of good labs out there. But our roots are really very unique. And I think every institution has a DNA, if you will. They have they have DNA that comes from their past, and it really does carry over into what you see today. All the national labs are like that. The roots of our national lab are very much, I like to think about it, rooted in engineering research. Okay, it's not necessarily, you know, science per se. It's engineering research. It's how do you build things? How do you scale? How do you understand what works, what doesn't? How do you operate those systems? And then what science needs to go back in to the feedback loop? That's our role. And we've done this in nuclear energy since that first frontier that I talked about. Every major advance in what you see today as commercial nuclear energy had some touch point on the Idaho site. So just 210 miles north of you. Every single one, from the first Navy reactors, boiling water reactor, every reactor type and class, the materials especially, the regulatory environment that went into regulating what is today a global industry, that all touched and still touches the Idaho National Lab. And there's some exciting stuff coming up that I'll show you here in a minute. So what that history left was left and actually has been built upon quite a lot is a huge set of infrastructure. You go out to the 890 square miles and you see little mini sites that look like small towns. And they're small towns that were set up basically to do these different parts of that nuclear energy mission. But that's being deployed now across nuclear energy, but also national security programs. It's a really very important part of the national capability for a number of different purposes. It's really a neat, quite a neat place to be. So, past, present, and future. Let's start with nuclear energy from the standpoint of, 70 years ago, like I mentioned earlier, you didn't have any of the infrastructure that you had. You didn't have any regulatory construct. You had actually a lot of hype about the potential for nuclear. Who remembers or has read about a reactor in every backyard? Do you remember that? Read some of the history, and that was seriously, people talked about that. So there's an enormous promise for this high density energy source. So why was that? Keep in mind the world that we were in. So when I was born, which was little after this, there was 3 billion people in the world, okay? When the first commercial nuclear plant was built, shipping port that I mentioned, there was 2.8 billion in the world, Okay, very different world. 130 quads total energy consumed. Just coming out of World War II, rapidly growing economy globally, not just in the United States, big load demand, right? People wanted lots of electricity dropped down in big chunks, and there was a demand for it, right? Rapidly growing economy, energy security was a thing back then as well. And nuclear energy was seen as a path to energy and economic security in that context. Remember that context. Fast forward to today. So in November, the projection is by November, the world will cross the 8 billion people mark. Think about that. Just in the time frame that we built this nuclear energy enterprise, global population is almost tripled. Energy demand has gone up by, what is that, a factor of 3, almost 4. And it's shifting. The types of energy that we use are shifting as well. Much more electricity, and that's going to be a trend for the future. Today, it's not a brand new industry anymore. And this is really important to remember as people talk about advanced reactors being deployed. You'll hear, hey, these are experimental technologies. We should worry about this. Well, maybe you should think about it. These are not brand new technologies, okay? This is 70 years into what today is over 400 reactors operating all over the world, producing 20% of our electricity, 10% of global electricity. And the context in which these plants are operating are very different. The economic, regulatory, environmental contexts are all vastly different. Okay, world 8 billion people. Now we look to the future. We look to 2040 and beyond, projections on the order of 9 billion people in the world, very different load demands. The need for big drops, at least in many parts of the world, big, huge power plants has diminished. Those are still required in many places, not so much in others. Climate change is a constraining finally a recognized constraining aspect that's being put into policy, into the tax code, and being driven by capital markets, quite frankly. The approach to climate change is being driven more by capital. So this is really very important to consider where we were 70 years ago at the first frontier and where we are today and where we're going. Because you do have a mature global nuclear energy industry now. Like I said, 20% in the United States. It's projected that globally it's about an $8 trillion market just in the next 20 or so years. So $8 trillion market. And I'm trying to think what size of market commercial aircraft are. I think it's on the order of 15 trillion in that same time frame. So think of the scale that you have today. Again, starting from nothing 70 years ago. So what's different? I mean, the reason we talk about the context actually gets to the point of why you're hearing about different types of reactors. And many times, the types of reactors that you hear about that might be suitable for today and beyond are different than the last reactors in terms of size. Yeah, there's different classes, styles of reactors as well. Just like there are different types of cars. They're all cars, but there's different models. And you buy a car to match whatever it is you're doing, whether it's traveling on the highway or somebody like me who's going out camping in the mountains and needs something different. Same thing with reactors. So let's take a look at the general classes of reactors that you're going to hear about. So existing reactors, very large, generally very large power reactors, right? They have very, on the order of, of thousands of megawatts, 1,000 megawatt a unit. Some of them that are being built in Asia are now 1,800 megawatts, and that's electric. So in terms of heat energy, it's, you know, almost three times that amount. They're enormous machines, heat producing machines. These are, and I'm sorry, Sid, I'm going to say light water reactor. These are water cooled and moderated reactors. They're generally, most of those are high pressure systems. So a lot of pressure, a lot of energy, big, massive construction projects. This is a photograph of the Vogel plant that's had just no end to the construction difficulties in Georgia. They're massive construction projects. This was the largest construction project in the country at the time. Very large reactors have very large safety exclusion areas because of the energy density and the pressures that you operate at. So you have emergency planning zones that are 10 miles, you know, I think, yeah, usually 10 miles around, you know, 1,500 acre footprints. So this is your grandfather's reactor, and this is what was developed, and this is really the backbone of the global nuclear energy enterprise. Okay, and we can talk about why these type of water reactors and why did those develop, not these other ones. But if you have questions in that area, let's cover it. Okay, so big reactors. Then you started hearing about small modular reactors. And not all small reactors are modular, but all modular reactors are small. I think that's accurate. So ponder that for a while. So small modular reactors started to get into really, well, let's say they came into vogue. A lot of interest in these because of a few different reasons. Number one, constructability. So the notion was build these in factories, unit by unit, you know, 80 megawatt sort of modules, stamp them out in a factory, roll them to a site, you know, do all your earthwork and your civil construction, and then start placing these reactors one by one, you know, as you needed it. This was a vision that was painted to you 25 years ago, right? And I'm gonna get to that in a minute too, because remember that. I'll give you a hint. None of this is new. None of it's new. So there's a cost advantage. Okay, you didn't have to take on a $10 billion construction project. Remember that. Okay, at best, these, you know, if you've got a 1,000 megawatt reactor, and they cost, if you're really doing well, $4,500 a kilowatt installed. These are multi-billion dollar projects. A lot of risk, you're tying up a lot of capital, you're paying a lot of interest, and you're waiting for it to come online. So small modular reactors, much smaller, stamp them out. They're standardized in form, but there's also some really important, what people like to call, and I think is an adequate term, inherent safety features that come with these small sizes. So they respond to off-normal events through the physics of the machine, not necessarily relying on engineered systems. And that's where you want to go. So you're flying an airplane and the engines go out, you want to be able to glide that down, okay, without doing much. These are even better than that because you shut off cooling and they rely on natural circulation. So the notion is you cannot get something like a Fukushima event where cooling water shuts off and within hours you have a problem. So modularity, inherent safety features, cost, okay, affordability, investability, efficient use of capital, the dollars that you have to play. They also have very small footprints because of the individual nature of those reactor cores. So you go down to a 50-acre site. And I believe these are being licensed or will be licensed with an exclusion zone at the fence of the facility. So no need for these 10-mile safety evacuation zones and things like that. NuScale is the example, the shining example, which has gone through licensing, NRC licensing. Actually, it's interesting with NuScale. You know how the NuScale design got started? So it was a laboratory directed research and development project. Those are internal lab funds. It was a partnership with our predecessor lab, the Idaho National Engineering and Environmental Lab, and Oregon State University. And fast forward, that was 20 years ago. That's how long this stuff takes to get into place. So big reactors, custom built reactors. Now you're going to small reactors that are, you know, stamp out these individual modules, put them in, again, a fixed facility. And it's for economics, operability, and matching generation to load and safety. You can always improve. Now, this is the area I'm most excited about. And it's microreactor. So what is a microreactor? It's a small reactor that's less than about 50 megawatts. Okay, so they're very small. Now, why is that important? So microreactors can be used for all kinds of different types of applications where you're not going to build a 1,000 megawatt reactor. You're not even going to build, you know, one of these, 6 modules of 80 and 100 megawatt reactors. You want 20 and 50 megawatts at a time. Now, where might that be? Well, if you're a chemical plant and you want to start reducing your carbon emissions, you can start plugging in 50 or less megawatts of heat at a time with microreactor. Let's say you're in a mining application. Lots of mines being sited to mine critical minerals for batteries now. Huge interest in microreactors to power those mine sites, which tend to be 10 to 20 megawatts at a time. Alaska, Canada, even remote areas in the West. Microreactors also can be put in what's called a nuclear battery configuration. So you can think of these as being able to be plug and play. I think of that potential sort of like my phone. So the phone has a battery in there. I have no idea where it's at in there. I just, I set it on a pad, it recharges. I don't have to change battery anymore. It's an integral part of this process. So your communications has gone very modular, and the energy source was embedded. That's how microreactors are viewed for industry, for industrial applications. And I'm going to mention a really exciting program the Department of Defense is doing in this area and why. Okay, so you went from big to smallish, you got to stack up lots of them, to really small, and possibly in some of these cases, more like a battery where you just bring in modules, you plug them into an industrial process, and then when they're done, you don't refuel them, you just take them back and you refurbish them, put a new one in. That's a microreactor. So you're going to hear about microreactors. You will hear about them here soon, because they're going to build one out at our site within 2 years. SMRs, you're hearing about the first deployments in the US are actually going to be at the Idaho site, but by a private company, which is UAMPS, which you're familiar with. And then the very large reactors are still a need for those, right? There's areas of the world that are growing that have demand for big chunks of power that you need to plop down. Yeah.
It's not classified in the size of the reactor in an aircraft area.
the last that I've read, they're 60 megawatt ish. Yeah, and there's a number of them.
Obviously, operate right next to it.
Yeah, you do. I mean, there's so the question was, if you couldn't hear it, what are the size of reactors that are in, for example, aircraft carriers, or in some parts of the world, some operate icebreakers with, submarines. So these have been running microreactors have been in one form in these defense applications for 60 plus years. So, but you point to another point that's really very important. None of these classes of reactors, although you're hearing more about them, and people might tell you, oh, they're experimental and brand new. They're not. So we operated microreactors out on our desert in the mid to late 1960s. There was a microreactor that powered the Panama Canal Zone until 1970. 73, somewhere in the 70s. There was a microreactor just east of you in Wyoming that powered a radar site for 10, 12 years. So these have been around, okay? It's not new. What's new are the materials. There's new materials, there's new fuels, very robust fuels, and there's new electronics. How you can monitor and control and operate the system. So this is a really important point. Different sizes now, none of those classes of reactors are new, and you have operated those. So this is the way I like to think of where we can be going with energy, and not just with reactors. You started with very large reactors. Actually, you started with small reactors, but they got very large. Now, people were interested in small reactors, so get the same energy output, but have a number of those. And now we're thinking about, how do nuclear batteries fit into this picture? So just like battery cells in an electric vehicle are put together, many different cells. You don't have one monolithic cell, right? Same thing is being looked at for powering industry with microreactors. But think of the implications. These are, $5, $6, $7 billion at a shot projects. These are hundreds of millions of dollars, and those are a magnitude less. So if you're an investor, you think about that. Also, there's very significant safety implications for that. So let's talk about that. But I want to talk about the fuel cycle first, because you should be asking, many are probably asking, well, how do you fuel these things? What are you going to do with the materials from the used fuel? So the fuel cycle, you'll also hear about the fuel cycle, right? The nuclear fuel cycle. And people will talk to you about different parts of the fuel cycle and what might be a problem and what isn't. But it's really fairly simple. So you dig up uranium, and natural uranium is 0.7% uranium-235, and that's the stuff you need to really operate many of these reactor types, right? So you got to enrich. First, you have to mill it, mining, and that's the conversion. Then you enrich it in uranium-235, and there's 2 enrichment sites in the U.S. But the U.S. has really dropped behind the curve on uranium enrichment. We've been importing most of the enriched uranium that we use in our fuel cycle, and that's an energy security issue. Then you make it into fuel. Then you put it in the power plant, and you use that. Undergoes, a process of reactions for a number of years, 3 to 5 years. And then when it's declared spent, and it's spent not when you use all of that material that's in there, it's spent when you build up so many other materials, right, through the reaction process that your reactor doesn't operate efficiently anymore. Okay, and that's declared spent. Now, the amount of the uranium resource that you actually use up in a nuclear power plant, a good friend of mine used to describe it like this, like taking a log, throw it in the fire, you burn the bark off, take the rest out. That's basically about what you got. And then what do you do with it? Well, in this country, all of that I just described is called a once-through fuel cycle. You take the used fuel, you put it in a water pool, you let it cool off because it's thermally hot, right? It's so much radiation coming off of that, you got to cool it down for a number of years, couple of years, few years. And then you can take that and it's ready for disposal. And today you keep that on site, and I'll show you what an on-site storage cask looks like. Other parts of the world will take that, they'll put it in a long-term permanent repository, just like you do other wastes from industry and other things. You segregate it, keep it. Some other countries, Japan and France, reprocess their fuel. So they take that burned, that log, you just burn the bark off, and they reprocess so they can utilize the remaining part of the material. That's reprocessed. And we don't do that in this country. And we can talk about why if you're interested. That's actually a long history. So that's a fuel cycle. So you're going to hear about fuel cycle, right? People are going to point to different parts of the fuel cycle and say, well, what about, we don't have enough uranium to enrich, or we don't have enough enrichment, or what do we do with the used fuel? And those are all very good questions, and they all have answers or challenges. So I do want to point something out, because a critically important part of this, what do you do with used fuel? And every energy generation technology that we have has a waste stream, every one. So solar energy has all the mining, processing, manufacturing waste, and then you got to do something with the cells after 20 years. You got to do something. Some of it's hazardous, some of it not. So in nuclear, it's a very high density energy source. The benefit in that is the waste from it is also really dense. So this, and I think this picture just drives home the density question. This is almost 30 years of operating, I think, an 800 megawatt reactor in Connecticut. That's all of the fuel, the used fuel waste. And you can see the people standing there for scale. And that can sit there in those casks. If you want to come out to the lab sometime and see a cask like this up close and personal, you can walk up to them, you can touch them, and they just sit there. But that's all of the waste over 30 years. And a good friend of mine at the Nuclear Energy Institute, he likes to do the comparison of waste streams from burning a pretty clean source of energy with natural gas, fairly clean. The CO2 that it would put off in a volume sense would fill up the Superdome 3,000 times. So you're going to have a waste stream anywhere, but that's what you get from 30 years of operation. So trends. I mentioned my cell phone analogy with energy. Lots of different products and infrastructures are going from big fixed, set in the ground infrastructure like power, like electricity generation, and they're going to more modular forms, more transportable, more investable, more manageable. And you see this, I think computing is a great example. Computing's gone from big you know, building size mainframe stuff to, well, this is my computer. This is what I use. Why do I bring that up? Because size does matter. And if you start talking about modular or micro reactors, you can begin to think of different applications when you go from big fixed infrastructure to more nimble, smaller infrastructure. So let's talk about size, because this is really a differentiating characteristic of what you see today versus what you saw 25, 30, 70 years ago. Now, size does matter. So why did we get so big with these power plants, so expensive on nuclear? Why did you go to 1,000 and 1,800 megawatts in one plant? By the way, you know, when you shut down a 1,000 megawatt nuclear power plant, you know how much heat is still generating? Shut down. 7 megawatts. So that's enough for how many thousand houses if you produce electricity with it? Tens of thousands. I mean, they're big. That's good. So why did, in a sense, how'd you get there? Well, it really was, it was the learning process from 50 and 60 years ago when we started with 80 megawatt plants. That was the first reactor, commercial reactor. Then you got larger. You started wanting to capture efficiencies. People will say economies of scale. It's really not economies, it's efficiencies of scale. So you get bigger, you pay less per megawatt, right? So you get bigger, build them bigger. It's all good. There are implications to doing that. I mean, you can manage, clearly, we manage those implications, but the safety systems on these water-cooled reactors get really significant, right? Because they're high pressure, very high pressure systems, very big systems. The engineered safety systems have to work, which means you have to have redundancy, right? Because you can't just rely on one if you have a safety class system. So they get really critically important. Now, remember what I told you about modern reactors operating on passive safety features. And I'm going to give you an example of that in a minute. Safety systems are bigger. They are not modular. Folks, you're not building those in a factory and shipping them out to wherever you want to ship them. These are unique construction projects. And if you're a finance person or you're managing that site, you worry about that because every delay is costing you millions of dollars, tens of millions. In the case of the Vogel plant, billions of dollars. They're big and complicated. And this is something people don't think much about. Where do you need to drop 1,000, 2,000, 4,000 megawatts of power in this country? Not as many places as you did back in the 60s and 50s, okay? You need more bite-sized chunks in many places, not all. So you can have a mismatch between generation and load. So as the industry matured, you just got bigger and bigger because it was more cost effective to do that. But advanced reactors are trending. We talked about the different sizes, but they're not just trending smaller for those reasons we just talked about, but they're trending what's called integrated, and they're trending modular. So integrated simply means you're combining a bunch of the mechanics within one vessel so you can build it in a factory and ship it somewhere, right? And they're getting modular. Modular means you're going to add 1 module, 2, 6 modules to get whatever power output you want. And that's really important. Now, the other thing that you're going to hear about is coolant types in the reactors. And this kind of freaks people out sometimes because you'll hear about molten salt cooled reactors. You're going to hear about water cooled reactors. You're going to hear about sodium cooled reactors. You're going to hear about gas cooled reactors. And Sid will tell me, as he did about an hour ago, why do I care? And I don't even know what that should mean. Now, in a sense, that's actually, that is the right response. These are just different classes of reactors, just like, you might drive an Audi, I drive a Ford truck. They're different mechanics, but they're still all getting you down the road. They're reactor types. But you are going to hear about these. Why are they using different moderators? Safety characteristics that go along with them, and efficiency in terms of thermal efficiency that you can get at them. They're just more efficient, and they're easier to operate because they have passive safety features. And that's why people are going to these. Are these new? No, I actually grew up working in that area. Those reactors operated successfully just north of you for 30 years. And then were decommissioned and demonstrated the entire process. So they're not new, but you're going to hear about these coolant types, and they're just different types of, like I said, cars. Okay, for safety features, the ease in safety, they're all safe reactors, but this makes safety easy. But the size, the efficiency, and these coolant types allow you to do different things. And this is the exciting part. So this is a frontier. So what can you do with these different types of machines? And I would argue the most important thing to think about is how you can embed these to clean up industrial processes. So if you're worried about carbon emissions in the atmosphere, so electrical generation is just a portion. It's actually a smallish portion. I shouldn't say small. It's a sizable portion of emissions, but industry accounts for over a third of all carbon emissions. So the question is, how can you take these bite-sized pieces and embed those in industrial processes, whether it be cement, steel, chemicals, mining, you name it? How can you expand the use of nuclear? And that's a frontier. That's one of the frontiers. So the ability to modularize creates a circumstance where you can just buy as much power as you need. When you need more, you buy another module. You don't have to plop down $5 billion at a shot, or a utility, or all of us has to pay for that collectively. Now, there's another thing I wanted to point to, and I keep saying this because it's so important. None of this is brand new. Okay. There's lots of Department of Energy demonstration programs that have an enormous library of data on all of these reactor fundamentals of these reactor types. Now, I want to point out one class, because you're going to have one of these, not the breeder variety, but you're going to have a sodium cooled fast reactor operating about 100, maybe 120 miles from 150 miles. How far is Cameron? About 150 miles. And I've heard people say, oh, that's going to be an experimental reactor. We don't want to be, experimented with our energy. It's fundamentally the same reactor that operated in Idaho up until 1993, 30 years. And this is just an example of a number of different demonstration projects of reactors that I'd encourage you to go and take a look at. Okay, look and see what was done. This in particular was important because what they demonstrated was industrial safety. Can we handle sodium well for decades? Does it perform well? If there's an incident with it, can we take care of it? Yes, on all those accounts. How does the fuel work? So the fuel, something called metal fuel type, which really increases the safety margins and efficiency in reactors. That was developed and demonstrated. Actually, you toured some of that back in the day. It's the same type of fuel that's going to be used in the new one that's going to be deployed commercially. Most importantly, that system, through its operation, they demonstrated, this isn't theory anymore, they demonstrated with that reactor plant, the whole plant producing electricity, full power. They demonstrated inherent safety. So what did they do? They initiated the two worst accidents that, well, two of the worst accidents that you think about with a nuclear reactor. You shut off the coolant, right? No more coolant flowing over the core without taking the energy down. And it's two different sequences. So basically you're doing what happened in Fukushima, where the reactor was operating, all of a sudden you lost power to coolant pumps, and what do you do? Okay, so they did that. They just shut off the pumps. There was about 150 people. Actually, my advisor at the time was at that test, sitting on the turbine deck when they demonstrated this. And you know what the reactor does? Because of the fuel type and because it's sitting in a sodium bath, that's its coolant, the temperature immediately spikes up from about 550 to about a little under 800 degrees. Okay, the boiling point of sodium is 900,000 degrees, so it's well below boiling point. Because of the fuel, the temperature spikes up. There's no damage to the fuel. The fuel, it's called Doppler broadening of cross section. So if you're a physicist, go take a look at that. But it's the physics of the fuel shuts the reactor down. And then it sits in that sodium pool and convectively cools on its own. You can just leave it there forever. So that's inherent safety. So they demonstrated that. You can actually watch a videos of that. So it was 1980s, mid 1980s, they did that. So this is really important. Why do I tell you? There's 70 years of reactor demonstrations in advanced reactor types, fuel demonstrations, you know, where we actually run things to failure just to see how far out failure is. But demonstrating inherent safety is a really important part of the future. So that's demonstrated here. So when you hear about these reactors and you ask questions, remember to go look up what's been done. That was a cool place to work, by the way. If you have a chance to work in a place like that, definitely go do it. Okay, so what's happening in the future? So different reactor sizes, you're going to hear about different fuel types, you're going to hear about different ways to cool the reactors. They're all advanced reactors. They have inherent safety features, but the sizes allow you to match it to the present need. So what's going on in the future, and this is actually what amazes me, is a number of different demonstrations that have been put into motion. And this is a timeline, and some of these dates are slipping. This reactor, I think it's actually going to go on in 2024. This is something our lab is doing. I call it, and I call it sort of a, well, it's a testing reactor. I call it a toy reactor. I mean, it's super small, kilowatt scale. So it's really meant to exercise some processes to build the machines, but some research will be done on it. The one I want to really call out your attention to is this Project Pele. So notice that's in a transportable form. It's on a truck. The Department of Defense is just down selected the company to build that. Pieces of it are being fabricated right now. It's going to be put together at the Idaho site and operated to demo that in 2 years. And it's being built to power the increasing power demands of military operations. So everything's going electric from directed energy sort of devices to just everything. And the logistics tail of shipping fuel to places just creates too much uncertainty going forward. So that's a really exciting thing because that's going to get built. That'll be the first advanced reactor that's built. Now, the company that's building that has come out and said they're going to build a commercial variant of that. So I start to think about industrial applications. And when you bring that together with where capital markets, investors, where policy and public opinion is forcing people into low emission manufacturing, low emission industry, that sort of thing is going to be really important to power that, because that's a high density energy source. And then, by the way, that is a nuclear battery configuration. So if you don't have need for the energy, you need to take that away. You can take it away. It's not in the ground infrastructure. And that brings me to the next part of the frontier that I think is really exciting. It's meeting this world of 8 billion people under the economic reality of having to go. It's not just the policy reality, it's not just climate reality, it's an economic reality where we will go low emission. And low emission products are going to be not just favored, but demanded. And that's at 30% of CO2 emissions that I worry a lot about. That's industry. So what if you could mix and match your reactor types, size your units so you don't waste so much capital in one shot? You could better size your energy system to the process so you could get to this sort of embedded energy and process, just like you have in your phone. And that would be exciting. So a nuclear battery, and I give credit to Sid, these were my co-authors on the paper that you mentioned on nuclear batteries. So our friends from MIT. So the nuclear battery configuration has a reactor that's in something that looks like a Connex box. It goes in the back of the truck. It has a power conversion container. It has instrument control container. Up to 20 megawatts of heat. I say up to 50 megawatts if you can get to that point. Standardized design. You're stamping these out in a factory, right? With fuel. And it really changes the paradigm. How does that? Just the size is what's mind-boggling to me. So if you think about powering an industrial process, say you only need 10 megawatts. There's a 10 megawatt wind turbine. By the way, you don't get 10 megawatts out of that. You know that, right? You get usually 3 functional on average. So here's a nuclear battery size. There's a 10 megawatt solar. And there's that little green thing is a nuclear battery. So the size comparisons, and I also have some tables on mass of materials used on each. It really is striking. So the notion is that you use these depending on the fuel type, lots of stuff we can't discuss in the time we have, for up to 10 years. So you don't refuel on site. So what does that do for you in this competition for low emission manufacturing and power for remote communities and remote operations? Think about it. Think about the research that still needs to go into it. And I think the instrumentation and control, remote operations centers. I think about a reactor leasing company that leases these and has an operations provider that just comes in, provides energy, say to, I don't know, company X that's operating in, Eastern Utah. And they're going to lease you an energy source, they're going to operate it. They have a big operations center, say, based in Salt Lake City that operates 100 of these all over the world. That's what I think about. By the way, that's sort of the model of jet aircraft engines right now, right? You lease engines, you monitor those all over the world in flight, out of flight. same model. And that can be applied to a number of different industries. So here's an example with metals manufacturing, and I'm cognizant of time, so I'll try to hurry up here. But it can be applied across industries. Some of these folks did a study in the Northwest to see how many industries could take one or more of those modules, and it's an enormous number of industries, from food processing and carbon intense industries to chemicals manufacturing, all kinds of different industries. But you got to make it simple. You got to make it easy. Data centers are something that comes to mind. Glass is actually a regional interest right now, glass manufacturers. So I'm going to leave you with that context. Remember where we came from and how we got to where we're at today, and those types of reactors, but most importantly, the types of applications. And likely in the future, a true frontier is, how do you think about expanded use of nuclear energy in this smaller reactor, advanced reactor configuration? But remember, you're going to have these advanced reactors in the 2 to 8 year time frame built within, you know, a couple hour drive of you. So you're going to hear about this. Ask questions. You've got an enormous resource at the university. Always contact the lab for perspective. We're not selling anything, right? The lab doesn't sell stuff. We actually work with all of those reactor developers and manufacturers to help them with fuels, help them with data. So hopefully we can give you an unbiased, but certainly, you know, perspective. But we do see the landscape through the lens of what's been done, what is being done, and what could be done. And there's still a lot of cool research to be done, I think, on the application side, not just on the reactor side, which I think is the reactors are pretty well worn. So I'll leave it there.